Start.
Thank you. Let's start. At today's last lecture of my course, I would like to consider some applications of spherical varieties to geometric and representation theoretic problems. Since it is the last lecture and I have not much time, I have to be selective, and I have chosen to discuss a representational theoretic problem of tensor product decomposition. So yeah, so what is this problem about? Let, as usual, G be a connected reductive group. Connected reductive algebraic group. Suppose we are given two irreducible representations of G, say of highest weights lambda and mu. So we have in our notation, we have V of lambda and V of mu. These representations are irreducible, but their tensor product, it is also a representation of G. It is no longer irreducible in general. And the problem is to decompose this tensor product of two irreducible representations into irreducible summands. Decompose this into irreducible G modules. This is a classical problem in representation theory. And here is a geometric approach to this problem. So the approach will be as follows. Recall that by Borel-Well theorem, we can realize each irreducible representation of G in the space of sections of some line bundle over a flag variety, G over B, where B is the Borel subgroup. And even if we are lucky, if the highest weight of this representation, say this lambda is a character of the Borel subgroup, but it may be extendable to a bigger parabolic subgroup. If it is so, then this V of lambda, the representation of G of highest weight lambda, is realized in the space of global sections of some line bundle over a partial flag variety, G over P over some parabolic subgroup. So we can realize V of lambda as the space of global sections of some line bundle over some G mod P. P is a parabolic subgroup in G. It may be a Borel subgroup, but in general, it may be some parabolic subgroup. And similarly for the second irreducible representation of highest weight mu, it can also be realized in the space of global sections.
Professor.
Yeah. Yes?
This is realization, not just inclusion, right?
No. We know by the Borel-Well theorem that the representation in the space of global sections over a generalized flag variety or partial flag variety is irreducible. So the representation in here is irreducible. So it is not inclusion, it is just equality. And similarly for the second irreducible representation, it can also be realized as the space, as a representation in the space of global sections over some other partial flag variety, G over Q, of some other line bundle M. These geometric realizations are always possible. Now consider what is called a double flag variety. So let me denote by X the direct product of G over P and G over Q. These kind of varieties are called double flag varieties. Double flag variety. And over this double flag variety, we have a line bundle. Let me denote it by script N, which is what is called the outer tensor product of the line bundles L over G mod P and M over G mod Q. The sign for the outer tensor product is this one, cross in square, not encircled, but in squared in a frame. What is this outer tensor product? It is a line bundle whose fiber over any point in this double flag variety. So this point is a couple of points, X in G mod P and Y in G mod Q. So the fiber of this N over this point X comma Y is just by definition the tensor product of the fiber of L over X and the fiber of M over Y. This is the outer tensor product of two line bundles on the factors of this double flag variety. And now the space of global sections of this line bundle N over the double flag variety X is just the tensor product. The tensor product of the spaces of sections of L over G mod P, which is V of lambda, and the space of sections of M over G mod Q, which is V of mu. So we get just the tensor product of V of lambda and V of mu. And in this tensor product, we have a highest weight vector. In this, better to say, in this space of sections of this line bundle, which is the tensor product of two other spaces of sections, we have a highest weight vector S naught, which is just the tensor product of the highest weight vectors in here and in here. So let me denote them by S sub lambda and S sub mu. These are highest weight vectors in these irreducible representation spaces, or in other words, they are B semi-invariant sections of this and this line bundle of the respective highest weights. And this S naught, as I said, it is a highest weight vector. Of highest weight, lambda plus mu. In the additive notation. In the multiplicative notation, it is, of course, the product of these two characters. Okay? Now, let us recall that for a spherical G variety, we have described the G module structure of the space of global sections of any line bundle over it in terms of some polytope associated with the divisor of some of these sections, of some of highest weight vectors in the space of sections. And in our situation, this gives us, let me turn to the next page, that if the double flag variety X is spherical, if the action, so maybe better to say, if the action of G on the double flag variety X is spherical, then by the proposition which we have proved at the end of the previous lecture, we get that the space of sections of this line bundle N, which is just the tensor product V of lambda, tensor V of mu, is isomorphic as a G module to the direct sum of simple G modules of highest weights nu, where nu runs over the shift of the polytope P, the polytope which was introduced, the polyhedron which was introduced at the previous lecture, at the end of the previous lecture, shifted by the weight of this section S0. So this is, the weight is lambda plus mu. Lambda plus mu. And this is a shifting vector for the polyhedron P, which is corresponding, this polyhedral domain is corresponding to the divisor of the section S0, this one, yeah? But we are interested not in the whole polyhedron P, but only in the lattice points in this polyhedron. So we have to intersect this with the weight lattice of X. Okay. So this tensor product, in case where the double flag variety is spherical, this tensor product is decomposed as a multiplicity-free direct sum of simple modules. Each occurs only once in this direct sum of simple G modules corresponding to highest weights from this set. So essentially, this set is the set of lattice points in some polyhedron, which is of course bounded in this case because this space is finite dimensional. Okay. So if we have a good control over the geometry of X, if we know the color data of X, then we can compute this polyhedron because it was given by inequalities, by explicit inequalities. Let me maybe show you from the previous lecture, just to remind you what was the statement. I mean this proposition, yeah. So this decomposition of the space of global sections of a line bundle of a spherical variety as the set of as the direct sum of simple G modules corresponding to eigenweights, to highest weights in some polytope. Yeah, and this polytope is given by the inequalities here, just by linear inequalities corresponding to each linear inequality corresponds to a b-stable prime divisor in X. Yeah, and these mi's are the multiplicities of these divisors in the divisor of the section S0, a fixed global section, or even a rational section. You can take even a rational section, a fixed section, B semi-invariant section of this line bundle. So this I just recall. I hope you have this in your notes. And let me come back to my situation. So in my situation,
the polyhedron region P here is determined by the section S, right?
By the section S0, which I denoted by S0. So this polyhedron, let me say, this polyhedron is determined, so polyhedral domain determined by the divisor of S0. And S0 is this section in our case. Okay? So if we have a good control over the geometry of X, over colored data and so on, then we can compute this polyhedron. And we can write down explicitly which highest weights of irreducible G submodules occur in the decomposition of the tensor product. And also this decomposition is multiplicity free because the action is spherical. So this can be done efficiently in many cases. And let me give you an example. I will consider just a very simple example in which, of course, the decomposition is known by other theory. But this example is quite clear, I hope, and at the same time, it is already instructive. So I hope that.
Professor, sorry,
yeah.
I want to ask a question.
Yeah. Please go ahead.
So I remember that the Borel-Weil theorem tells us that a homogeneous line bundle over a generalized flag variety is a simple G module. I mean,
exactly. The space of sections.
So do we have that any homogeneous, any G line bundle over a generalized flag variety is homogeneous? Do we have the converse?
I would say that how to say. I mean, yes, it is homogeneous because actually, you can. The group which acts faithfully on the generalized flag variety is the adjoint group. So the center of the group G acts trivially on the generalized flag variety. So what acts faithfully is the adjoint group. The adjoint group acts faithfully on G mod P. But the action of the adjoint group of G may not lift to L. You have to take a finite cover. But you always
but L is a G bundle. How can a subgroup of G does not lift to L? I mean.
If you start initially with some irreducible representation of G, then it comes from a G line bundle. But if you take any line bundle over G mod P, then it may happen that G itself, the action of G itself, cannot lift to L. But what can be always lifted to L?
I mean, if we have the line bundle is a G bundle, then do we have that the bundle is homogeneous? I mean this.
Well, homogeneous, let me say, G bundle is more or less, this is a terminological issue. What is, I think that I defined a homogeneous bundle as just as a G line bundle over a homogeneous space. It is homogeneous in the sense, it is not a homogeneous space. It is a homogeneous line bundle in the sense that the action of G permutes the fibers of this line bundle transitively. It is homogeneous in this sense. The action is homogeneous on the fibers.
Yes. I mean this.
But this is just because it is a line bundle over homogeneous space. So the base points are permuted transitively by G, and therefore the fibers of L are also permuted transitively if the action lifts. So maybe this name is confusing, homogeneous line bundle. Let me just say that it is a G line bundle. It is just the same thing in this.
I see.
Okay.
So the L and M here is a homogeneous line bundle, right?
Yes. L and M are G line bundles, or in other words, homogeneous line bundles, which is the same over these homogeneous spaces. Yes, of course. Okay.
Okay.
So let me come back to this example. So in this example, the acting group G will be just GLN, the basic example of a reductive group, GLN. And we consider the representation of GLN in some symmetric power of the standard representation. So we take the, say, mth symmetric power of the column vector space K to the n, on which GLN acts in a natural way. Okay? So we consider this kind of representations, and we want to decompose a tensor product of two of these kind of representations into irreducible modules. So this will be the problem which I am going to solve in this example. And for convenience of computations and for convenience of resulting formulae, it will be more convenient for me to consider the dual representation. So a representation not in this space, but in the dual space. In other words, this symmetric power of k to the n star is just the space of homogeneous polynomials of degree m in coordinates on k to the n. So this space, the m symmetric power of k n star, is the space of homogeneous polynomials of degree m in n variables, on which GLN acts by a linear transform of variables, by linear transforms of variables. This adding a star is harmless because if you prove something about these dual representations, if we find a tensor product decomposition, for instance, then taking the duals, we can turn back to the initial representations without this star. So we shall consider this kind of representations for convenience. The symmetric powers of the dual of the standard representation. This is an irreducible representation. Yes.
The symmetric power just means homogeneous, right?
Yes. Essentially, as I said, this is just the space of homogeneous polynomials in n variables. These variables are coordinates on k to the n, nothing else. So this representation is irreducible. And we can indicate a highest weight vector. It is just the nth coordinate, xn, to the power m. This monomial of degree m in this vector space is B semi-invariant because when GLN acts on Kn, the standard Borel subgroup of upper triangular matrices leaves the last coordinate unchanged, maybe only multiplied by some factor. If you consider the action of an upper triangular matrix on a column vector, you will see that the last coordinate will only multiply by something. So the last coordinate considered as a function on k to the n is B semi-invariant. And the eigenweight of this last coordinate is minus epsilon n. So epsilon n is the last diagonal entry of a diagonal matrix or of an upper triangular matrix. So this epsilon n is the eigenweight of the last basic vector in k to the n. But when we act on the dual space, then we act by inverse transform of an argument of a linear function, and the sign changes. So this representation is irreducible. It is irreducible of highest weight minus m times epsilon n. Okay. So this is the highest weight vector. Let me write it here. Highest weight vector. And what is nice, why I prefer to consider a dual representation here, because this representation has a clear geometric meaning in the spirit of what we discussed here. This representation has the following geometric meaning. It is identified, this space is identified with a space of global sections of a line bundle over the projective space of dimension n-1, which is just, line bundle of over the projective space of dimension n-1, which is just the projectivization of this vector space k to the n, the line bundle of degree m. So the line bundle usually denoted by O of m. The space of sections of this line bundle is exactly the space of homogeneous forms of degree m in the coordinates, in the projective coordinates on this projective space. So these projective coordinates are exactly x1, xn, and the homogeneous forms in these coordinates form this vector space, the symmetric power, the m symmetric power of k to the n star. So this is the geometric realization, which is a particular case of a realization of this kind, because the projective space is an example of a generalized partial flag variety, an example of a partial flag variety for the group GLN. Okay, so now we want to decompose a tensor product. So say take S kth power, kth symmetric power of Kn star tensor with Lth symmetric power of Kn star. And we want to decompose this tensor product into irreducible representations of GLF. So according to the strategy which we described right before, we can represent this tensor product as a space of sections of a line bundle over the product of two copies of Pn minus 1. So Pn minus 1 cross Pn minus 1. This will be my double flag variety X. And we take a line bundle over this double flag variety, the product of two copies of the projective space, which is the outer tensor product of two line bundles of this form. So we take O of K, outer tensor product with O of L. And this will be my line bundle M in the previous notation, which I consider over my double flag variety X. This will be N. Okay? And in this tensor product, in this space of sections, we have a highest weight vector S naught, which is just the tensor product of highest weight vectors of these two tensor factors. So the highest weight vectors are of this form, but they are taken with respect to so we have to take projective coordinates on each copy of this Pn minus 1. So if we denote a point in this product variety as a couple X, comma Y, so that X and Y are just points in Pn minus 1 in here, then this section will be just this highest weight vector will be just the product Xn to the power K times Yn to the power L. Okay? And the highest weight is, of course, so the highest weight is, of course, the sum of the highest weights of these two factors. So this is minus K plus L epsilon n. Okay? This is our initial data. And now we want to apply this formula. We want to compute some part of colored data of X. Namely, we are interested in the weight lattice and in B-stable prime divisors. And we want to compute this polyhedron P. Well, let's do it. There are the following. Yeah.
I have a question. So, you pick up a section from for example OK, and then a section from OL, right?
Well, these guys are just highest weight vectors. They are unique. Because these are irreducible.
So what is the product here? A tensor product or
well, you may consider you may write a tensor product here, but you may also consider this as a product of coordinates. I mean, for instance, you may
is precisely the product of function of coordinate functions.
Because let me finish. Because these two factors are polynomials in different sets of variables. The sets of variables x1, xn and y1, yn are not intersecting, and therefore the tensor product of two polynomial algebras in variables xi and in variables yj the tensor product of these two polynomial algebras is just a polynomial algebra in the whole set of variables. So we may consider this tensor product of these two factors just as a product of these polynomials in the big polynomial algebra. This is the same under natural identifications.
Maybe I should say that so your line bundle is not a tensor because they are theoretically they are line bundles on different varieties, right?
Well, this is an outer tensor product. It is not an inner tensor product.
Yes.
It is an outer tensor product.
Yes,
So
yes.
you may say
The line bundle is the tensor product of two pullback line bundles.
Yeah. This is what I wanted to say.
Okay.
You may consider this as a usual tensor product, but you have to take this line bundle and take a pullback on X along the projection to the first factor. And also this line bundle can be pulled back on X along the projection to the second factor. And then after you have taken these pullbacks, you may take the usual tensor product of these line bundles over X. This is the same.
This is clear.
Okay, very good.
Thanks.
You're welcome. So let's compute in part. Let's compute the part of color data which we need for tensor product decomposition, for the tensor product decomposition. So first, we need to describe the b-stable prime divisors on this X. So what are b-stable prime divisors on X? There are the following divisors. So let me turn to the next page. So b-stable prime divisors. So first, you may take two b-stable prime divisors pulled back from the factors of this double flag variety. So let me denote them by D1. D1 is given by the equation xn equals to 0. So essentially, we have the divisor. We have a prime divisor on the first factor, p to the n minus 1, and then pull it back, take the whole inverse image of this divisor on the double flag variety, on the product of two copies. And similarly, we have the second divisor, which is of the same form, D2. It is given by the equation yn equals 0. But there is yet another b-stable prime divisor, D3, which is not a pullback. It is given by the following equation. Let us consider the determinant of the last two coordinates, of the last two projective coordinates of x and y. So this determinant xn minus 1 xn, this is the first column, and yn minus 1 yn. This is the second column. And this determinant, let me denote it by delta of x comma y. So the third b-stable prime divisor is given by assigning this delta to 0. Clearly, this delta is a b-semi-invariant homogeneous polynomial, irreducible homogeneous polynomial in coordinates x1, xn and y1, yn. And therefore, it defines a b-stable prime divisor on the product of two copies of Pn minus 1. So these are b-stable prime divisors on X, and the defining equations are given by the sections of the corresponding line bundles. Because observe that these coordinates xn and yn and this determinant delta, they are not functions on X, because the projective coordinates are determined only up to a multiple. So these guys are sections of line bundles. These are homogeneous polynomials in projective coordinates. So they are sections of some line bundles over Pn minus 1 cross Pn minus 1 over X. And also observe that the divisor of our canonical section S0, which we have chosen here, the divisor of S naught, is just k times d1 plus L times d2. Okay. These three divisors actually are the only b-stable prime divisors on X. So it is a complete list of b-stable prime divisors on X, because we can prove that the complement of the union of these divisors in X, so X minus the union of d1, d2, d3, is just a single open B orbit, which we usually denote as Y upper naught. So the claim is that this complement is a single B orbit. Of course, it is open because it is a complement to a union of finitely many divisors. The claim is that it is a single B orbit. It is quite easy to see it. Let me prove it, because I want this example to be absolutely clear to all of you. So let me prove it. So what I want to prove? I want to prove that if I take any point in this complement, then I can move it to one and the same point by applying some transformation from B. So let us take such a point. For instance, let me denote this point as before as x comma y. So let me take a point x comma y. And what I can do first, I can take the first component of this point, the first component of this pair. So this is just x. X is a point in the projective space with coordinates x1, etc., with projective coordinates x1, etc., xn. And now I want to apply some transformation from B to this point x and to put it to a canonical form, to move it to one prescribed fixed point, one prescribed point. Okay, so I want to do it under the assumption that this point doesn't belong to the divisor given by this equation, because I am working outside the union of these three divisors. So under the assumption that xn is non-zero, I can easily find such a transformation from the Borel subgroup. So I can find a transformation given by an upper triangular matrix, which takes this point x to the following form. So all coordinates except the last one will become 0. And the last coordinate can be taken to 1. So let me denote this point for brevity as x naught. X naught is not a coordinate of x. It is just a point, a different point. Okay? So since when you are considering an action of upper triangular matrices on column vectors with these coordinates, then if the last coordinate is non-zero, then you can easily move any column vector with the non-zero last coordinate to this form. Okay? And also the stabilizer of this point x naught in the Borel subgroup B. So the set of all upper triangular transformations which preserve this point x naught is clearly of the following form. It consists of matrices of the shape like this. So let me draw it for you. So something like this. Excuse me, let me do it better. Excuse me.
The
Yeah.
left up piece is a broad subgroup of order n-1, right? That is
you are right. Yeah. You are anticipating what I'm going to write. I just spent some time on drawing because it is, yeah, let it be like this. So what is this stabilizer? So you have anything here, any non-degenerate upper triangular matrix here. Okay. You have any non-zero entry here. So you have something here, something non-zero. You have zeros, of course, here, and you have zeros in the last column, except for the last entry, and you have zeros in the last row, except for the last entry. So this is the shape of the matrices of the upper triangular matrices which stabilize this point x0. And now I want to put the second component of the pair xy. So we have this point xy. I want to put the second component y to a canonical form. It is also easy to do this. So if you have a point y, which is maybe, let me do it here. If you have a point y, which is again a tuple of projective coordinates considered up to a multiple, y1, etc., y n minus 1, yn. Then we want to put this y to a canonical form. But at the same time, we do not want to destroy this x0. So we have to act on y by the stabilizer of x0. And we do it under the condition that our point does not belong to the union of these divisors. So we assume that these equalities become inequalities. So we do it under the assumption that yn is non-zero. And also this delta is non-zero. And the first component is already taken to the canonical form. So the first component is this one. Now it is easy to see that first of all we can obtain that the first n minus 1 coordinates, this first n minus 1 coordinates, can be put to this form, to the similar form, by the action of this block of size n minus 1 by n minus 1, and this will not destroy the first n minus 1 components in here. So we can take this. Since we assume that yn is non-zero and delta is non-zero, this implies. So just look at what is delta. If yn is non-zero and delta is non-zero, so we have xn minus 1 is already 0, and xn is 1. So this determinant is non-zero, means that yn minus 1 is also non-zero. So let me write it here, that this implies that yn minus 1 is also non-zero. And therefore, we can put the first n minus 1 coordinate to this form.
First n minus 2, I mean.
No, n minus 1. First n minus 2 will become 0, and n minus 4 will become 1.
Is 1.
And the last coordinate is controlled by the action of this non-zero entry by multiplication. So here we may put any non-zero entry, of course. And also we can just, yeah, so here we can put any non-zero entry, and we can make this coordinate yn equal to 1 also. So finally, we shall put this point to this form. Let me denote again this prescribed point as y0. Y0. Okay. Okay. So what we have proved? We have proved that any point in this complementary set can be moved to one and the same point, namely the point which is the pair x0, y0, by applying some element of b. So first we apply b here, some element of b here to put x to this form, and after that we apply some other element of b from here to put y to this form, but this form will not be destroyed when we act by this element, because this is a stabilizer. Okay, so we have proved the claim that this complement is indeed a single b orbit, and therefore we have found all b-stable prime divisors. There are no other b-stable prime divisors except for these three. Okay. In particular, this implies that X is spherical because there is an open b orbit. Hence, our X is spherical. Now I want to compute the weight lattice of the spherical variety X. Let me turn to the next page. So for the weight lattice, I can say the following. Let's consider the set. Yeah. Okay.
Do we have that Di is not G-stable so that they correspond to the colors?
Exactly. Well, the only case in which D3 is so D1 and D2 are never G-stable, but D3 can be G-stable if n equals 2. So if there are only two coordinates or for x and y, then this determinant will be G semi-invariant, and the divisor will be G-stable. So if you have the product of two copies of P1, so n equals 2 means we are considering P1 cross P1. Then on P1 cross P1, this D3 will be indeed G-stable. This will be just the diagonal.
So D3 is not a color in that case.
For n equals to 1, D3 is not a color. But for n equals to 2, D3 is not a color. But for n greater than 2, D3 is a color. Because this homogeneous form is not G semi-invariant, only B semi-invariant, if n is greater than 2. Okay?
I see.
Well, yeah, okay. So now I see that actually the break time comes. So maybe I will postpone the description of the weight lattice after the break. Let's make a break in time. So if you still have questions, then you may address your questions to me. But anyway, now we have a 10 minutes break. I will switch off my microphone, but if you have questions, then do not hesitate to ask. I will switch it on again.
So there is no need to consider n equals to 2 because the boundary on P1 is clear, or we have to discuss.
Well, you are right. It is good that you remember that actually this problem, which we are considering, this tensor product decomposition problem, is a generalization of the one which we have discussed on the very first lecture. It is a Clebsch-Gordon decomposition formula, which gives you a decomposition of this kind for n equals to 2. And we considered, if you remember, we considered, we proved the decomposition formula in this case for n equals to 2 by exactly the same geometric method which we exploit now. But for this simplest situation, we did not use the theory of spherical varieties, which we know now. We just use some elementary arguments which are possible in that case. Well, in fact, they are possible even in this case, but I want to give you this example a bit more complicated than the one from the first lecture. I want to give you this example as an illustration for this method, for this general method, which of course can be applied to more complicated examples, but they are not suitable for discussing at the lecture, so maybe this simplest example is enough. I will give you also exercises with more complicated examples, not too complicated, of course. So you will try by yourself. Okay. Well, so let me mute my microphone for a while. And anyway, I'm ready to answer questions. Well, let us continue with this example. So I want to compute the weight lattice of this double flag variety, which is the product of two copies of the projective space. And to this end, let me consider the semi-group of B semi-invariant rational functions on my X. And let me take any function in this semi-group, say of eigenweight nu, whatever it will be, I don't know so far. It is a function in xy, which is B semi-invariant with eigenweight nu. So since this function is B semi-invariant, the divisor of this function is B stable. So the divisor of this function f nu is a linear combination of this d1, d2, d3. And this means that the function itself can be expressed up to a multiple as a product, or it's better to say a ratio of sections corresponding to these divisors of sections of line bundles corresponding to these divisors d1, d2, d3 to some integer powers. So this function should be of the following form: xn to some power k1 times yn to some power k2 times delta of xy to some power k3, so that the divisor of this function will be k1 delta 1 plus k2 k1 d1 plus k2 d2 plus k3 times d3. But since this product is not just a section of the line bundle corresponding to this divisor, it is a function, there are some restrictions on the exponents, on the powers, k1, k2, k3, because this f nu should be a true function in x and y. It cannot change if you multiply the projective coordinates by one and the same multiple. And this imposes the following conditions. So since the first factor is of degree k1 in xn, the second factor is of degree k2 in yn, and the third factor is of degree k3 both in x and y, in coordinates of x and y. So in order to to keep this expression unchanged, when you multiply x, all coordinates of x with one multiple, and multiply all coordinates of y with another multiple, the following restrictions should hold. So we should have that k1 plus k3 and also k2 plus k3 should be equal to 0. So the homogeneity degree in x and y should be 0. And these are these two equations. From these equations, it is easily seen that all functions which are B semi-invariant, with respect to the Borel subgroup B of upper triangular matrices, all functions of this kind are actually of the following form. They are you have in a sense a minimal one of these functions. So you may take let me write it as xn dot yn over d. This is the minimal function, the function with minimal exponents of this form, with these restrictions. and all other functions are just powers of this one. So this function, it generates the semi-group of B semi-invariant rational functions modulo scalars. And the eigenweight of this function can be computed easily, because what are the eigenweights of xn, yn, and delta? xn, yn, and delta. The eigenweight of xn is minus epsilon n. So maybe I write it like here. The eigenweight of xn is minus epsilon n. The eigenweight of yn is also minus epsilon n. And the eigenweight of delta is this determinant. So when you act by, say, a diagonal matrix, by the inverse of it, because you act on the argument by an inverse transformation, then this determinant will be multiplied by the inverses of the last two diagonal entries. So the eigenweight of this delta is minus epsilon n minus 1 minus epsilon n. These are the eigenweights of these factors in the numerator and the denominator, and therefore the eigenweight of the whole function, so it is a function of eigenweight, let us compute. So we have minus 2 epsilon n in the numerator, and minus epsilon n minus 1 minus epsilon n in the denominator. When you divide, then the weights subtract, so you get the following. You get epsilon n minus 1 minus epsilon n. This is the eigenweight of this function. And this function is a generator, as I already explained. In other words, we get that the weight lattice is generated by the weight epsilon n minus 1 minus epsilon n. Actually, this weight, which I will denote just for brevity, I will denote standard notation alpha n minus 1. It is the n minus first simple root of the group JLM. So this is the standard notation. Alpha i's is the standard notation for simple roots. So this is the last one. There are n minus 1 simple roots, and this is the last one, which is this difference. Okay, so this is the weight lattice. Also, we can describe the vectors. So recall that we have the vectors vi corresponding to the B-stable prime divisors. These vectors are in the space, well, even in the dual lattice lambda star, which is again of rank 1, and it is spanned by the covector, by the dual weight, which is dual to this alpha n minus 1. I will denote the generator of this dual weight lattice in the following way: alpha n minus 1 star. And what are these weights? So what are these vectors? To compute these vectors, you have just to evaluate the order, the vanishing order of this function, whose weight is generating the lattice lambda. You have to evaluate the vanishing order of this function along these divisors d1, d2, and d3. And you see from this formula that the vanishing order of this function along d1 and d2 is equal to 1. So this function has a 0 of order 1 along d1 and d2. This means that the first two of these vectors, v1 and v2, are just alpha n minus 1 star. While the last B-stable divisor, d3, So our function has a pole along D3, a pole of order 1. So the last of these three vectors, the vector V3, equals minus alpha n minus 1 star. Okay, so we have found the vectors corresponding to this B-stable prime divisors. And now let me describe the polytope P. Maybe on the next page, it is better to do it on the next page. So the polytope P consists of all vectors, say nu, in the space generated by the weight lattice. So in the space generated by alpha n minus 1, the Q vector space generated by alpha n minus 1. So such a vector should be a multiple of alpha n minus 1. This m is a rational number, but later on I will be interested in integer multiples because I am interested in lattice vectors, in lattice points of this polyhedron. But so far m is a rational number. Maybe let me write it here. M is a rational number. We take the vectors nu of this form, which satisfy the following inequalities, the defining inequalities for this polyhedron. So the defining inequalities are the following. So the pairing of each of these vectors v1, v2, v3, of each of these vi's with the weight nu, should be greater or equal than the respective multiplicity of the divisor di in the divisor of the section on the section S0. So in here you see the multiplicities. The first multiplicity is k, the second multiplicity is L, and the multiplicity in D3 is just 0. So the inequalities are the following. So the pairing of V1 with nu, so nu is this one, nu is this vector, this weight, and V1 is this vector. So the pairing is just m, equal to m. It should be greater or equal than minus k. This is the first inequality. The second inequality is about V2. So the pairing of V2 with nu, which is still m, because V2 and V1 is one and the same vector. But now the inequality is that is greater or equal than minus L, the multiplicity of D2 in the divisor of the section S0. And the third vector, V3, has a pairing with nu, which is now minus m, because V3 is minus alpha n minus 1 star. And the inequality is that this should be greater or equal than 0, because the multiplicity of D3 in the divisor of the section S0 in here is 0. So these are defining inequalities for P. And we see that in this case, P is just a segment on a line. So let me draw it for you to make it clear, to make it absolutely clear. So so we have this line. This line indicates the vector space generated by the weight lattice. So we have this line. Let us put the lattice vectors on this line, the lattice points. So this will be the origin, and these are the other lattice points. Okay, so this may be this first lattice point corresponds to the generating vector of this lattice. So we have this lattice lambda. And this is alpha n minus 1, the generating vector for this lattice. And now the inequalities defining P say essentially that the points belonging to P are the point for which this multiple is non-negative, because non-positive, because of this last inequality. Yeah, non-positive. So we have something on the left from the zero, something on the left from the zero, and on the other side, this multiple m is greater or equal to both minus k and minus l. So we get a segment. Let me draw it here like this. So maybe like this, but do it like this. Oh yeah, I mean something like this. This will be my P. Maybe I should do it more precisely. So it starts from here and goes up to 0. This is my P. Well, this point corresponds to, how to write? I mean, this is 0, maybe. Maybe I will put the coordinates above this line. So let me move 0 to the top. And this coordinate will be the left bound, the left limit for this segment will be, of course, minus the minimum of k and l. So all m belonging to all these m belonging to this segment correspond to this polytope P, polyhedron P, which is a segment in this case. So we have described P, and now we can conclude what is the tensor product decomposition formula. So the conclusion is that the tensor product of, maybe on the next line to save space, that the tensor product of the k symmetric power of k to the n star and lth symmetric power of the same space decomposes as the direct sum of simple GLN modules whose highest weights are of the following form. So the highest weights, nu, let me turn back to this slide, look at here. So the highest weights nu are of the form lambda plus mu plus a lattice point in this polyhedron P. So lambda plus mu in our case is this guy, minus k plus l epsilon n. So we have minus k epsilon n minus, this is lambda, minus l epsilon n, this is mu. And we have to add a lattice point in this polyhedron. So I will change the sign for convenience. So here m is non-positive, and I would like to change the sign. So for me, it will be convenient to have m non-negative. So I will write minus m alpha n minus 1. Yeah. This is a lattice point, so m is now an integer. This is a lattice point in this polyhedron. And if we recall what is yeah, if you recall what is alpha n minus 1, it is this difference. Then we get what we get. We get, I guess, the following. We get minus m epsilon n minus 1 plus m minus k minus l times epsilon n. So these are the highest weights of irreducible summands in this tensor product decomposition, and the restriction, the range for these highest weights is given by this polytope. This means that m should be in this interval, or maybe minus m should be in this interval. So we have the defining inequality that m ranges from 0 to the minimum of k and L. This formula is very similar to the Clebsch-Gordon formula from the first lecture, but it is more general, of course. Still, it is well known in representation theory. I mean, you do not need spherical varieties to prove it. There are many other ways to prove this formula, but I wanted to have this argument as an illustration of the general principle of how spherical varieties can be used to compute tensor product decompositions of this kind. So this is this example. Also, let me give you an exercise with a bit more complicated examples. So, so the exercise is to decompose into the direct sum of irreducible representations. The following tensor products of irreducible representations of reductive groups. So the first exercise is to decompose the representation of the symplectic group Sp to n in the tensor product of two symmetric powers of k to the power 2n. So this exercise is very similar to the previous example, but the acting group is now not GLN, but the symplectic group. And the answer will be more interesting than here. If you solve this exercise, you will see the answer. So there will appear two parameters. So here everything depends on a single parameter, m. So everything lives on a line, yeah? And in this case, there will appear two parameters, but you have to solve this exercise to find the precise formula. And the second example is again about GLN, but now the exercise is to decompose into irreducible representations of GLN the tensor product of two wedge powers of the standard representation. So in our example, we considered symmetric powers, and now let it be wedge powers. This is also a very standard formula in the representation theory. It can be proved in many ways, but the exercise for you is to prove it using this method, using spherical varieties. So maybe I have to add it here. So yeah, use spherical varieties. Okay. Are there any questions on the example or on the exercises? No questions so far. maybe I will add a bit more about this tensor product decomposition problem. What I want to add is that, as we have seen, this method of decomposing tensor products works well if the double flag variety is spherical. Yeah. So here, what we have discussed here we did not use sphericality at this stage. So this is more general. But if you want to decompose efficiently this tensor product into reducible representations, so this is this space of sections of the outer tensor product bundle. If you want to decompose it into reducibles, then it can be done efficiently if the action is spherical. Not only in this case, also in the case, so-called case of complexity 1, but this I don't want to discuss. So in the spherical case, it can be done. And this was done, actually, in all possible cases. Let me comment on it. So, yeah.
Well, I want to ask something about the polyhedron region. Well, in this example, the polyhedron region is bounded. Do we have it always bounded?
We have it always bounded if the variety X is complete.
Oh,
for instance, for the double flag variety, the double flag variety is complete, and therefore it is bounded because on a complete variety, the space of sections of any line bundle is finite dimensional. Okay? This is a general fact from algebraic geometry.
Yes, yes.
And if this polyhedron P were unbounded, then there would be infinitely many summons here, and this space would be infinite dimensional. So we can get an infinite dimensional space of sections only on an incomplete variety. So in the case which we are just considering, everything is finite dimensional and the polyhedron is bound. I hope it is clear. Actually, this is a criterion.
I know that.
Yeah.
Thanks. So if a G variety has every G bundle has finite dimensional sections, then it is complete, right?
If any line bundle on a G variety has finite dimensional space of sections, then it is complete. Well, I think that in the spherical case, the answer is yes, just as a corollary of some considerations. But if you want to ask me in general, then I have to think. I believe yes, but maybe there are some nasty exceptions. I'm not sure at the moment. I believe that the answer is yes in general. Even if you waive the G action, so if you have an algebraic variety, well, maybe smooth, just for safety. If you have an algebraic variety, smooth algebraic variety, on which every line bundle has a I'm not sure.
Since you just say that P is bounded if and only if X is complete,
No. I said a different thing. I said that P is bounded if and only if this space is finite dimensional. This is true, of course.
Yes.
But I'm afraid that this space may be finite dimensional even if X is incomplete. Not for spherical varieties and not for G-line bundles. This is just from combinatorial considerations. I think it is easy. Or maybe even not. Well, you may imagine something like this. You may consider a complete variety and remove just a single point from it. Then maybe there are not too many line bundles on this incomplete variety which do not extend to the whole complete variety. And maybe even there are no such line bundles when you are just removing a single point. So removing a single point will preserve the space of sections of all line bundles, but will make your variety incomplete. So maybe it is possible with such kind of counterexamples. I have to think about it a little bit more. But maybe it is possible that your variety is incomplete, and still all line bundles over it have a finite dimensional space of sections. Maybe it is possible, but if your variety X complete, then it is guaranteed that all the spaces are finite dimensional.
Oh, I see. Thanks.
Okay, you are welcome. So what I wanted to say to conclude this discussion about this tensor product decomposition problem, I wanted to say that actually spherical double flag varieties are classified. So spherical double flag varieties are actually classified. So the classification, let me write like this. So we have two problems: to classify spherical double flag varieties, and the second question is to compute all tensor product decompositions which are related to these double spherical varieties, to this spherical double flag varieties. So the classification, and the second part is tensor product decomposition. Computation of tensor product decomposition. So both problems are by now solved.
Oh, these problems are solved in the academic.
Say it again.
Well, you mean that these problems are solved in today's mathematics academy, right?
Well, yes, I just give you some names. So the classification of spherical double flag varieties was obtained by several people. So the first one was Peter Littleman. Who actually solved both problems, but in a particular case. So let me write like this. So Peter Littleman, in his paper of already 1994, solved both problems. So he classified spherical double flag varieties and computed the respective tensor product decompositions in the case where these parabolics P and Q are maximal parabolics in G. Maximal parabolics. For instance, the example which we just have considered belongs to this case, because the projective space, this space P to the n minus 1, is a partial flag variety for GLN. And the parabolic subgroup stabilizing a point in here is a maximal parabolic subgroup in GLN. So the example belongs to the Littleman list, of course. And also for each item in his list, in this classification list, for any pair of maximal parabolics for which the double spherical variety is spherical, Littleman computed all tensor product decompositions of irreducible representations, V of lambda and V of mu, such that the highest weights lambda and mu extend to characters of these parabolics. So they are realized in the spaces of sections over G mod P and G mod Q. And the general classification without this assumption was obtained later by John Stambridge. In 2003. So John Standish classified all spherical double flag varieties, and separated from the previous. And the respective tensor product decompositions, all the respective tensor product decompositions were computed by Ponomaryova in a couple of papers. Of 2015, 2017, so quite recently. Well, this was the application of the theory of spherical varieties, which I wanted to discuss first. Actually, my plan was to discuss other applications. For instance, I wanted to speak about how the theory of spherical varieties can be applied to enumerative geometry. Coming back to this example with plane conics, if you remember from the first lecture, Steiner's 5 conic the problem of 5 conics. But I see that now I would spend yet another lecture to discuss enumerative geometry. I cannot do it in 10-15 minutes. So I think that it is a good time to stop now. I'm finishing my lecture, and I'm finishing this lecture course. So thank you all for your interest, for your attention, for your questions. I hope that you got some impression about the theory of spherical varieties from this course, the theory, which I believe is beautiful in itself, and it has many applications, of which I just touched a small part, of course. There are many more applications. But anyway, this was, for you, this was an introduction to the theory. And if you got interested in it, you may go further following the reading guidelines which I gave you some time ago, maybe here. Was it here or not? Yeah. So I gave you some time ago a reference list on spherical varieties in which some of the nodes are expository. For instance, the first one, and maybe this third one, and the other are of more survey type. So if you feel yourself already skilled in this theory to some extent, then I advise you to go to the paper of Perrin and the references they are in, and you may also look in my book, but as I said before, it is more general. Anyway, I hope that this lecture course was interesting and useful for you. And maybe during the last 5 minutes, 5-10 minutes, so we can discuss the exam. Also, by the way, if you have questions on this lecture and maybe some more general questions, you can address it to me now, because it is a good time now. We have time for questions. But also, I would like to say something about the exam for those of you who is interested to taking the exam on this course. But first, let me proceed with questions. If you have any questions, then maybe I'm ready to ask you to answer. I'm ready to answer. Any questions? Not yet. Okay. Then what I want to say about the exam. So Huhan, I don't know if he hears us now. Huhan, are you with us? It seems not. But we discussed with Huhan the procedure, the date of the exam and the procedure of the exam. So he told me that those of you, so he made a poll, a small poll among you, and he told me that those of you who would like to pass the exam prefer one of the dates, June 17th or June 18th. So this is a weekend, Saturday and Sunday. And the exam time will be, so the exam will start at 2 o'clock p.m. So 14 on, I have chosen the Sunday, June 18th. So let me write it maybe here. So exam. The course will be at June 18th, 2 p.m. The starting time is 2 p.m. So it will be distant, of course. It will be in VOOV meeting, where we usually meet. And the procedure of the exam will be the following. So first of all, we can call it the first part of the exam. It will be your homework.
In this meeting or another independent meeting?
No, let me explain. So let me first explain the procedure, and then maybe some questions will become clear, and the other you can ask. So the homework will compose, the results of the homework will compose the half of the grade, of the final grade. So I invite you to solve the exercises. I counted, there are about 47 or so exercises which I gave during the lectures, including the two exercises here, yeah, these two items in this exercise. So they are essentially two separate exercises, including these two. So there are about 47 exercises I counted. And maybe I will not require solving all of them. Maybe I will give you a list of about 20 exercises or so, one half of the whole amount, which are most essential in my opinion, and which I would like you to solve to get the grade on the homework. Okay. You may solve these exercises and send me your solutions by email at any time before the exam. Well, maybe not before the exam, but before, say, well, exam will be on 18th of June. And let me put the deadline for sending me your homework at June 15th, for instance. So let me write it here. So send solutions to email by June 15th. So this is quite flexible. I mean, you need not send me all solutions once at the same time. You just do it step by step. Some of you already do this. So I have received several solutions to exercises, and I made some corrections and even sent it back. So the people made corrections in their solutions and send me corrected solutions back. So all this is possible. I mean, this is very flexible. So you have about 4 weeks, yeah, a bit less than 4 weeks. So today is May 17th and the deadline is June 15th. So you have a bit less than 4 weeks for doing this. And during these 4 weeks, you may send me your solutions. You may correct the solutions. I will check them. I will send you my remarks. You may correct your solutions and so on. So I hope that you have enough time to solve many exercises during this time. This is the first part of the grade, and you may call it the first part of the exam. And the second part will be on June 18th. Will be the theoretical part. Theoretical part. This will be oral examination. But with preparation. This will be on the exam date, so on June 18th. What does it mean? This means that we organize a meeting in VOV. You switch on, and you will receive randomly chosen theoretical question from the exam program, which I compose promptly in a few days. So you will have the exam program in a few days. So you will receive one question from this program, from this question list, for preparation. So you have to tell me everything about this question. I mean, if you if there are some theorems, you have to tell me what these theorems are with the proofs. So I assume that the proofs, you will also explain the proofs of the theorem. But for this, I will give you some time to prepare. So you receive a question at 2 p.m. You receive a question, and you will have, say, 1 hour for preparation. During this time, you prepare your answer to this question. So you write some paper, and you send me this paper on email, for instance, or maybe in the chat. I don't know if it is possible to attach files in the chat. This I will figure out with Kuhan. But anyway, you will send me your paper after this 1 hour expires. And after that, I will read each of your papers in turn, and we'll have an oral discussion. So maybe I will have some qualifying questions about your paper, about what you have written, what you have proved in this paper. And after that, after you answer these qualifying questions and explain me your answer, so you will get the grade. I will evaluate your answer. Is it more or less clear?
What is VOV meeting? I mean,
this is the meeting. I mean, I guess that this is the name of the conference client which we are using. This is the title. What I am seeing in my at the top of my window of the conference window.
well, we're still using
VOV meeting is the English name.
This meeting.
Yeah. So the meeting, the conference meeting, where we usually meet. This is the English name, you say. So the Chinese name is somewhat different. Okay. This is.
I mean, will we use the same meeting as we use now?
I think so, but this question should be addressed to Huhain, because he will be helping me to organize. I hope he will be helping me to organize this exam. He will be the moderator of this conference for the exam. Maybe he will organize a special conference. I don't know, but we have time to fix all these things. Maybe another meeting. This is not a problem. We shall fix all these issues. We have time for that. But I mean, the general exam procedure, is it clear more or less? So these two parts: first the homework, and secondly the oral part. With preparation for your oral answer. Is it clear, more or less? Do you have questions on the procedure? Well, it seems that so far there are no questions. Then basically we can finish. I just want to repeat that I think so about this homeworks. I think that in a couple of days I will collect a sub list of exercises which are mandatory for these homeworks. So of course you may solve all exercises, but some of them are similar to the others, so maybe it is too much. It is good if you solve all exercises, but maybe it is too demanding for you because you have other things to do, I think. So I think that I will choose some 20 or so of exercises and give a list of these exercises. I will send the list to Huhain, and he will put this list maybe on the disk, on the web disk where the notes of the lectures and the records are stored. Okay? And also, the same thing concerns the theoretical part of the exam, which will occur on June 18th. So I will compose the exam program. There will be a list of theoretical questions. I don't know, for instance, Sumihiro theorem, or maybe classification of simple spherical varieties, something like this. So there will be a list of questions. And when you come to the exam on June 18th, you will receive one of the questions from the list for preparation. So you have to prepare your answer to this question.
The question we receive is determined by us or by Professor?
No. It is determined neither by you nor by me. It will be determined randomly. So there will be a random choice. Some generator of random numbers will be launched, and I mean something like this.
Oh, I see.
Okay. So basically, you have to prepare all questions in principle, but on the exam, you have to know all questions to get a good grade. But on the exam, you will receive a single one, but chosen randomly.
Will we receive the question before the exam, or
at this time?
This means we will not know the problem unless the exam time.
Well, I mean, the exam starts at 14. At this time, you will receive the question. Then you will have, say, 1 hour for preparation.
So before this time, we will not know the problem, right?
Yes, you will know the list of all problems, but you will not know the problem which you will receive for the exam.
Oh, we will know the list of all problems. Oh, I see.
Yeah. But this will be not problems like to solve something. This will be theoretical questions, like to prove Sumihiro theorem, for example, or maybe some part of it. I will try to make these questions, single questions, not too big and not too complicated, because I understand that the exam time is limited. Okay? Is it clear? But what I want to emphasize that you should also know the proofs of theorems. At least, I mean, keep in mind, maybe some details could be missing, but still you have you need to have a general understanding of proofs, how things are proven. Okay? Maybe when you answer your basic question, maybe I will ask some additional short questions, but without preparation, just to understand whether you have a good understanding of the whole program, just to formulate some definition or some theorem without proof. This will be short questions without preparation, but this will be the very last part before setting the grade. Okay? Well, if there are no more questions so far, then we can finish. Let me stop sharing.
Okay. Thank you for your lectures in this semester.
Thank you for your attention. and I am expecting to receive exercises. So I advise you not to delay with it, because you know, some students try to put everything on the last day. If you decide to solve all exercises which you need at the last day, say at June 14th, then maybe you just have no time. You will have no time for that. But so I advise you to make it more flexible, to start just now. Some of you already started, but the other could start just now and send me your solutions step by step. So you solve several exercises and then send me solutions, and then turn next to the next exercise, and so on. So make it more flexible for you. This is my advice. Okay. Well, so thank you all, and I hope to see at least some of you on the exam. Bye-bye.
Goodbye.